with certain frequency with a periodic signal, we use an oscillator, right? We use an oscillator. Suppose this is being generated from an oscillator, this sine wave, and its frequency. We have two type of oscillator. One is generating fixed frequency oscillator, and one one can generate the variable frequency oscillator. It means that one can generate the different frequency depends upon the condition. Okay, so basically we have two type of oscillator: fixed frequency oscillator, and other one is voltage controlled oscillator. Okay, fixed frequency oscillator is generating only fixed frequency. Okay, but voltage control oscillators are generating a different frequency depend upon the depend upon the voltage that applied in the oscillator. Okay, this is voltage control oscillator and this is frequency control oscillator. So now concept is that why we are studying voltage control oscillator. The thing is that in our wireless communication, we have the voltages are always being changed. Okay, and we are dealing in different frequency spectrum. So depends upon the voltage value, the frequency are we need different frequencies at different amount of time. So that's why voltage control oscillator is quite helpful for us. Okay, here, hello. Are you there? Right?
Yeah.
Output frequency changes depending on the value of the control voltage input. Now coming to the application, that is the application that being used. We studied this. After that, we were dealing on the Borcation criteria. What is the condition for a signal to oscillate? It means that what is the condition in which we get a signal of a frequency, of some frequency. So for that, we studied Borcation criteria. Suppose we have an amplifier and here we have a feedback circuit. Okay, and this is amplifier of gain A j omega n. Condition of oscillation condition is that the gain of this whole circuit should be 1. It means that gain of open loop gain of this circuit is equal to 1. And apart from that, the phase angle of this system should be in the odd should be the either 0 degree or 2 n pi. Phase should be 2 n pi. Okay, but okay, and after that we have the LC oscillator, inductor capacitor oscillator. We have the quartz crystal oscillator. Every oscillator has its different advantages and disadvantages. LC oscillators have a very poor stability. Quartz crystal resonator are having good stability. Okay, so these we were dealing in the last class. Now coming to the phase lock loop. This is important. Phase locked loop. Okay, how the phase lock loop works. See, what do you mean by phase lock loop? Phase lock loop claims that if we have the input has a fixed frequency and phase, then the PLL do what? The frequency of the VCO, the PLL will track the frequency, will track the changes in the input frequency, and will try to adjust the output frequency according to the input frequency and phases. let's see how does PLL work. Suppose this is our phase detector. This is our low pass filter. This is our VCU. This is our V input. This is our V output. This is our PLL circuit. So what happens? We have the phase detector. What it do? It do. Suppose we have an input frequency of some we have an input of some phases. Okay, we have some input. We have some input frequency with not with without any phase. You can tell. Now you can see we have a we have an input frequency input signal here sine 2 pi ft plus phi in. This is our input frequency. And we have a VCO that is sine 2 pi ft plus phi VCO. So you can see how these phase log loops are changing the phases. You can see we have the input frequency of different phase. We have the voltage controlled oscillator output frequency of the different phase. This phase detector will detect the changes in the phase, and give a voltage. Okay. Difference of phases will be given by a voltage here, V delta, and that voltage is Kd phi in by phi VCO, that we can write Kd delta phi. Okay, and depends upon this voltage, depends upon this phase. This phase is supplied with LPF low pass filter and it being automatically fed to the voltage oscillator. These voltage oscillator are changing the frequency. So right now I told you that voltage oscillator is giving a different frequency depending upon the voltage that applied to it. So in that way, we are getting different frequency, and that frequency are the same frequency that the input signal have. So in this way, the phase lock loops are maintaining the same frequency by 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 giving a voltage. The phase detector are giving the voltage that it is detecting, that is proportional to the phase difference between input signal and VCO signal, and that voltages are converted to the frequency and that are fed to our system. So in this way it works. So let's see the example circuit. Do you have any doubt till now?
No.
Okay. This is our phase detector circuit. Let's analyze this circuit. This is point A. This is YT. So V input equal to sine 2 pi ft plus phi in, and VCOT equal to sine 2 pi ft plus phi VCO. Okay. Now we will measure the signal at A. How the phase detector will work. Signal at A. Sine A sine B equal to cos, that is phi in minus phi VCO minus cos 4 pi FT plus phi in plus phi VCO. And this signal will not pass to the low pass filter. We will have at the output after low pass filter, our output will be half cos phi in and phi VCO, that is half cos delta phi. Okay, and this delta phi, and we see that a log PLL will always naturally reside in one linear region. Okay, that yielding approximately. So in this way, this is working. Do you have any doubt that how the phase detector is working?
No. No, it's okay.
Okay. Apart from that, we have a digital phase detector also. It also works in the same way, but in the digital phase detector, we are using XNOR circuit. Okay, you know the working of the XNOR, right? How does the XNOR gate work?
Yeah.
Okay, that's fine. So digital phase detector works on the XNOR circuits. The way the XNOR circuit are working, in that way, digital phase detectors are working. Okay. After that, we have a phase lock loop logged state. We will study how the phase lock loop are working in logged state.
Hello?
Yeah, yeah, yeah.
Yeah.
So here we got this is low pass filter. We are assuming here that PLL is logged. What do you mean by PLL is logged? That this frequency is constant and it is equal to Fin. That we are assuming. Assume PLL is logged. It means that frequency VC is constant and is equal to Fin, but input phase is not equal to voltage control oscillator phase. Okay, so we'll have a phase difference, that is phi in minus phi VCO, and but this is constant. This phase difference is constant, and hence V difference is constant. Okay, and we will have low pass filter passes a constant signal and V out is constant. V out will be constant. V out will also be constant. And since V out is constant, the VCO is constant. So in this way, we achieved a phase lock loop of a system in which phase lock loop of system, and it is giving a constant VCO frequency. Now we will see the second case, phase loop as a stable, whether this is stable or not. If imagine we have some positive noise get added here. Suppose a noise get added here. Okay, then V out will get increase. Noise get added here, V out get increased. Frequency of V out VCO also slightly get increased. Okay, as does phase will also decrease, and the phase difference will decrease slightly. Again, V determinate difference will decrease slightly, and this V determine decreases slightly, and it helps in the to make it and it make the that PLL stable, unstable. So that is the in this way we are saying that if noise is increasing, then the loop act to reduce its back gain, and in that way it is making it stable. Okay, because this is the feedback. Right, and to it V out increase slightly and V did decreases slightly. We did in the slide 21, if you'll see in the slide 21 that if V difference are decreasing slightly, there is nothing, it will be in the linear region only and system will be stable. Okay. Okay, that's these are the examples. If we have a K naught is 2 megahertz per voltage, VC frequency are from low pass filter gain is 5. If the loop is locked to an input frequency, what is the controlled output? Let's see here. K into V delta T. Yeah, are you seeing the page number 33? Can you see the page number 33? We have question there.
Yeah.
Yeah. Are you able to understand this question?
Can you explain it, like solve it for me first? So, 'cause I'm not sure. Hello?
Yeah. Do you know how to solve this question? Do you have any
No,
idea?
can you
Yeah.
explain,
Yeah.
please?
Yeah. You can see if the loop is locked to an input signal at 440 megahertz. Okay. And we have VCO frequency F naught equal to 450 megahertz and K naught equal to 2 megahertz per volt. Okay, K naught is 2 megahertz per volt. Okay, that is the output frequency sensitivity, and we have this much. Okay, and KA is, if the loop is logged to an input signal, it means that F in FCO FCO equal to F input. Okay, and that is 450 megahertz. What is controlled output voltages at this signal? You can see 2 megahertz per volt. It means that in 1 volt we can have 2 megahertz. So they are asking that 440 megahertz, 2 megahertz per volt, and they are asking at 240 megahertz. So let's see at okay, 1 volt, and then 1 megahertz will be half volt, then 440 megahertz will be 220 volt, and that will be divided by voltage gain is 544, and that will be here the control voltage is needed to be 0. Can you tell me why? Because here it is in locked state. Are you getting my point? Are you getting my point?
No.
Let's see. What does phase lock loop do? Phase lock loop do, suppose we have the difference, suppose F input and FCO, okay? And we have some phi CO and phi in. And phase detector will give you KD and phi in minus phi VCO. It is passes to a low pass filter, and that is again given to VCO. Okay. FCU F in and FCU are same, it means that the difference, now I told you, this difference will be always a constant value. Then if that is same, then this difference will be always a constant value, will give you a constant value. Then your output will be always then your VCO output will be always give you 0, because we do not need to control the output, because it is only in the logged loop. Are you getting my point?
Okay.
Okay, any doubt till now?
No.
Or we will take up some more example on this one, that will clear your all. If you have the doubts, then it can clear those doubts. There is no issue. Okay.
Okay.
So, okay. Now you can see PLL example. The XOR one. What is the phase difference between two input signal at the phase detector? two inputs to the, what is the phase, as a phase is logged and input signal is 440 megahertz, what is the phase difference between the two input signal? Let me check. Yeah, this question I will take up once completed. Other topic is the logged range. What is the log range that we have to find? What is log range? The input frequency range over which PLL remain logged to the input signal. That is when frequency of VCO output continues to track the input frequency, that is known as log range. Are you getting what is the log range?
Yeah.
Suppose let's see here. Suppose this is your frequency, okay, and this is your F naught, and this is your range of phase detector. Now we have VCO adjustment range. If the input frequency range over which PLL remains locked to the input signal, that is when frequency of VCO output continues to track the input signal, that is known as log range. Okay, here the log range can be limited by either minimum or maximum voltages of phase detector times K naught. This is the logged range. Okay, oscillator range of the VCO, we need to complete all the limits, and yeah, this is the log range. Okay, now we can tackle one question example, that PLL example. We have F naught equal to 440 megahertz, okay, and frequency range 515 to 575 megahertz. Particular voltage gain equal to 5, phase detector output voltage equal to 3 volt. What is the lock range here? Okay, they are asking what is the lock range here. So basically you have to find, we have the frequency range from 415 to, this is our frequency, suppose this is 415 to 475. Okay, now voltage from the phase detector times K, lock range can be limited by the other minimum or maximum voltages from the detector. The minimum voltages is 5 times the K naught. Okay, so log and F naught is 450. This is for 415 to this one. So we can have the lock ranges. We can have the lock range, that the phase detector, the maximum phase detector that can generate the values, and that we can add it. You can see our lock range will be 2 megahertz into 5 into 3, that will give you 30, here 30, and that is plus minus 30, and you can see it is the 60, it is from 60 megahertz and it is 450. So the lock range will be around the 420 to 475. Lock range we can calculate from 420 to 475 megahertz because at the input side we have the deviation of the 5 megahertz, because here the voltage gain is 5. Okay, do you have any more any doubt here?
I didn't really understand how we got
Sorry,
that. I didn't really understand how we calculated that.
I'm not getting your voice. Is equal to 2 megahertz, then 2 megahertz, that is 30, that is 1 over and 60, that will give you 30 megahertz. Okay, that will give you 30 volt times 5, 30 volt times 5, that will be 10. Okay, okay, ask me, do you have any doubt then?
I said I didn't really understand how to do this.
Okay, okay, let's see. Okay, before that we can again go to the lock range. What does lock range was telling to make you understand it? See, the input frequency range over PLL remains logged to the input signal. Okay, input signal locked to, and that is when frequency of VCO output continues to the track the input. So the lock range can be either the minimum or maximum voltages of the phase detector times Ka times K naught. Are you understanding this part?
Yeah. Hello?
Yeah. I'm just getting it. The log range can be given by K naught AP pi. Okay, and here K naught is 2 megahertz. To 5. These 15 30 megahertz. This 30 megahertz, 30 megahertz. 30 megahertz into pi divided by 2 pi, and that will give you, that is 60. If you calculate it, 2 into 5 into 3 into 60 divided by 2 pi, that is 900 megahertz. Is 5 into 3, that is 15 pi. Try in this way to just make you understand. Frequency sensitivity is given 2 megahertz. Frequency sensitivity is given that is F naught. Okay, and frequency sensitivity 2 megahertz per volt. Frequency sensitivity is 2 megahertz per volt. So for phase detector frequency will be 6 megahertz. That will be plus minus 6 megahertz, and that will be multiplied by 3. That will be 30 megahertz. Okay. Now you see this output can goes up to 480 megahertz. Are you getting it or not?
Yeah.
Are you getting it?
Yeah.
Because here the phase detector can detect up to 30 megahertz. Are you getting it? How I calculate 30 megahertz? 2 megahertz into 5 into plus minus 3. So it will go plus minus 30 megahertz. So it will track from 440 to 480, and here up to 420. Are you getting the point or not?
No, I didn't get how you got
But
30.
yeah, 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 yeah. But 480 is out of the range, so it will get limited up to this point. You didn't got how
No,
to
I don't understand how did you get.
yeah. So first I have to find phase detector frequency. Okay. So phase detector frequency is can be how can we find? We have the frequency sensitivity given. Okay. Sensitivity given, that is 2 megahertz per volt. Okay. And the range can be decided, that I am telling that the range can be decided by this 2 megahertz per volt into Ka, the voltage gain, and phase detector output, that is plus minus 3 volt. Are you getting it? And multiplied 2 megahertz into K. What is K? Plus 5. And this is what is the range of this phase detector output, that is 3 volt. Are you getting 30 megahertz or not? You are getting?
Yeah.
Or not? Okay. So plus minus 30 megahertz, right?
Mm-hmm.
Right or wrong? So from F naught, you can deviate up to plus minus 30 megahertz, right or wrong? So you can deviate up to 420 and 480 megahertz, right?
Yeah.
But frequency range is up to 475 only. See the question?
Mm-hmm.
Frequency range is from 415 to 475. So what will be the log range? Log range will be 420 to 475, right or wrong?
Yeah.
Any doubt?
No.
Okay. So these was our, up to this we can have the log range. Okay. Any doubt, then please ask me.
No.
Okay. Now can we go to the capture range?
Yeah.
Now I think you can find this type of question. You can able to solve this type of question, right?
Yeah.
Just you have to convert that. Just you have to see how much you can have the range. That plus minus range you have to find, and you have to see where is your center frequency and go beyond that. Okay, plus minus of that one, and you can say whether it is lying in your range or not. If it is lying in your range, you can have those values in that one. Okay.
Mm-hmm.
Okay. Now you see capture range. The input frequency range where PLL can acquire log is known as capture range. Okay. Okay. And capture range is usually very less than the range of that one of log range. When compared to the log range, the capture range is very less. Okay. So that's the and let me give you. This is your F naught. This is a capturing input frequency over PLL can acquire log is known as capture range. Okay. Now we can see the capture mechanism. When PLL is unlocked with no input or where F input is far from VCO, the VCO run at its center frequency F naught, that is free running frequency, but is unlocked. We are now studying. The frequency of phase detector output is Fin and minus FCO, that is when unlocked. If the frequency is outside the loop filter bandwidth, the loop of filter output is 0. So control output is 0. VCO runs at center frequency, no possibility of VCO moving to input frequency, that stays unlocked. We can only acquire lock if input frequency is closer to F naught. Thus, Fin minus F naught must be as smaller than the bandwidth of the loop filter. So for the lock range, for the capture range, F in minus F naught is as much as small. This is as much as small. So it is in the lock range. Now after that, we have the PLL application that recover average frequency for FM demodulation it being used. These are the PLL application. Okay. Do you have any doubt?
No.
So with this way, you can have the finished of this unit 1, if I'm not wrong. And this version and the frequency. We can see one good example of the PLL examples. We have a phase detector, and we have a bigger circuit. There are many amplifiers like that, and we have a divider. We are dividing the frequency, and we have the FCO here, and here we are giving F reference. Here we have the F output. Okay, now we have F input equal to F reference. We have the F input equal to F reference, called the reference input. We add a frequency divider in the PLL after VCO. Now both input to the phase detector have the same frequency. Both input to the phase detector have the same frequency. We will have the the input from a no good source having the frequency and a frequency divider in a PLL after VCO. We have this is VCO, and so if we will have this type of circuit, then our F output will be n times of F reference, and that is giving you a frequency divider. So in this way, we can have the frequency divider, or we can digitally change the output frequency of ours by just changing this number. So this is a very good example of VCU. Okay. Do you have any doubt till now?
No.
Okay, that's good. Okay, this is your unit 1 completed. We can go to the unit 2 frequency synthesizer from, right?
Yeah.
Okay. You can revise this unit. Okay. We can take up the questions. We will try to take up the questions of these type of questions that came in your previous examination. In our next classes, I will prepare those questions and we will discuss those questions in our next classes. Right
Okay.
now, we can go to the frequency synthesizer, right?
Yeah.
Frequency synthesis, right? These two module you have, right? These two, the PDF that you sent it. Only this PDF is there in your syllabus, or do you have any more thing?
Sorry?
You have sent it two PDF, right? Two notes PDF, right? Do you have any more PDF, or this is
No,
a sorry?
I
Only that
don't.
much, right?
Yeah.
Okay. Yeah, that will cover all your syllabus, right?
Yeah.
Okay, that's good. Okay, now see frequency synthesis. We will take a brief of this one. When is your exam?
I don't know exactly, but it's in mid-December.
Okay, in mid-December. Okay.
Yeah.
Because 30-40% we have covered. We need, yeah, I think we need some more time. Okay. Here we have a frequency synthesis. Here we have a stable fixed frequency oscillator. We know fixed frequency oscillator is always give you a fixed frequency, and we want to generate a signal at a range of different frequency. Okay. So what does frequency synthesis do? It is giving you fixed frequency f output, but you want to generate a signal of different range of frequency. Okay. So that is frequency synthesis is doing. So with the help of the control, depending upon the control value, the f reference will be fed to this frequency, and depends upon the control value, the f out will get changes. Are you understanding it's working on it? Okay. Depends upon the control value, your f reference will always get changes, and it will give you that much f out. Okay. Okay. Let's see. We want to generate a signal at different range of it will. The solution is frequency synthesis. Generate one of many different frequencies. The frequency synthesis value, it generates one of many different frequencies. Okay, it generates one of many different frequencies. Okay. Now we will see all derived from one fixed frequency reference oscillator. These all derived from, we have one fixed frequency. See, what is the good thing of this? We have only one reference frequency, but even with we have only one reference frequency, we can have different control values, and it changes the output frequency. We will have the different frequencies, different output frequencies. So it can be taken care by two methods: direct frequency synthesis or indirect frequency synthesis. Direct frequency synthesis, we are using a frequency adder, subtractor like this, or indirectly we are using PLL that we studied right now. Okay, the direct signal frequency generates a sample of digital desired signal digitally. Now let's see here. Here our reference is 50 megahertz and we are getting output 150 megahertz. So how we are doing? We are multiplying by n. That is a nonlinear. We have a nonlinear element here. Okay, nonlinear element, and it generates different harmonics. Okay, what happens here? When your frequency passes to this, it generates different harmonics, multiple frequency it generated. Okay, and we use a band pass filter to select a desired frequency and it can pass. Okay, or we can divide by n and we can get different frequency likewise. Okay, and how we can do frequencies addition and subtraction we can see. This is your frequency addition and subtraction. Now, can you tell me what is the V output? Please tell me what is the V output? Hello, are you there?
Yeah.
Yeah. Can you tell me what is the V output?
I don't know.
Are you solving?
Yeah, I don't know what's the
Okay, okay. Then you can tell me. Yeah, because I'm just dealing because in this chapter you will get a lot of numericals. Just like the last chapter, in the starting part we did a lot of numericals, numericals type formulas. So this will also help you. So we will see. See, this is a frequency multiplier. This is a multiplier circuit. Okay. What happens? Observe things. If we are multiplying two signal of different frequency, we are adding the frequency. If you are multiplying the signal, you are adding this frequency. Just like observe it. Your V output is V12 into V22, right? So here you will get A1 cos 2 pi f1t into A2 cos 2 pi f2t. Here you are multiplying both signal. Okay. So you will get A1, A2 pi 2 into cos 2 pi f1 plus f2 t plus cos 2 pi f minus f2 t. Now you assume that your frequency, this input is 100 megahertz frequency. This signal having 100 megahertz frequency and this is having 50 megahertz frequency. Then you can think you are having 50 megahertz frequency and you are getting two output frequency. One is 150 megahertz f1 plus f2 and another is 50 megahertz. Okay. Now you observe a case. Just I have given you. Suppose this is your F reference and this is your control signal. Control signal is nothing but your V2, okay, and it is your V1, okay, and you are getting V output, okay. Here V1 frequency is fixed, that is 100 megahertz, and our F output is always F1 plus minus F2. Now you take a case that you are changing your control signal every time, then your F2 will be always changing, right or wrong? Then you will get a different frequency at the output. Are you getting my point or not?
Yeah.
Are you getting my point, Clara? Okay, so it is a filter that select either sum or difference, okay, and full multiple, okay, it is using in that way. You can see a good circuit of direct frequency synthesis. There you will get a good circuit, and we have the in the other page we have the indirect frequency synthesis, that is with the PLL. Okay, so in this way we are having the different frequencies generation. Okay, okay. Can you see the page number 13 and can you solve the question?
No, I don't really know how to solve this.
Yeah, that thing we already discussed here. See, I told you that we can have a different frequencies using a frequency divider also. Okay, so basically what they are asking, they are asking a range of n values that are required to produce an output having range. Okay, we have the output that are having from 450 megahertz to 440 megahertz to 450 megahertz. Okay, and we have signal f reference equal to 25 kilohertz. Okay, so just now we studied that f out is equal to n into f ref. Okay, now take case 1. When f out is 440 megahertz, okay, 440, then n into f ref 25 440 megahertz, 440 megahertz, n equal to 25 kilohertz. Can you tell me the n value now? Can you tell me, Clara, why solving it? Hello, are you solving? Okay.
17,600.
17600 you will get. Okay. Now take second case. When your F output is 450 megahertz. When your F output is 450 megahertz, you will again get what value that you have to find. 450 megahertz. So n equal to 450 in 10 to 6, 25 into 10 raised to 3. That will give you 1800 megahertz. 18,000 megahertz. 18,000 n value. And this is it. So which answer? Option number 1, right? Is the correct answer. Right or wrong?
Yeah.
Are you getting this question or not?
Yeah.
Okay. Now they are discussing the problems. If f reference is very small, We need large divider running at very high speed. The loop filter must remove the double frequency, so bandwidth must be very small. So these are the disadvantages, that are the theory part, that I'm not going into that one, that we can have the understanding of those theory part. And there are the alternative circuits are there. You can have the circuit in different manner, and please observe the circuit, how the circuits are working, that are important, how they have connected. You can see the alternatives method, that first we have the 1 megahertz circuit. Okay, 1 megahertz circuit is getting divided by 40. So at the input of the phase detector, you will get a frequency that is dividing by the 40. Okay, and at the other input of the phase detector, you will get 450 divided by n, and that those frequency will get added up plus minus, and that will pass to the filters. In this way it is working. Okay, now coming to the fractional and PLL, that is an important topic. Fractional and PLL. So we have here fractional and PLL. Here we have phase detector, and here we have a control logic, and we have then how does it between? We are using a high speed dual modulus divider using n and n plus 1, and we have control logic cycle of output. So we have a average division ratio here, average division ratio, that is 1 by r n plus 1 into k plus n r minus k equal to n plus k by r. This is your average division ratio. Okay, and r is the if every r cycles, r is the number of the cycle, n is the division, that what is the factor in which we are dividing it. Okay, okay, and for k cycle, in every r cycle it configures divider to n plus 1 for k cycle, and to divide n for remainder of the r minus k cycle. So in this way this fractional PLL is work. Okay, in this we can have a high speed dual modulus divider using n or n plus 1, and we can control logic count cycle of output. Okay, here minimum count is possible n, minimum divider possible n, and maximum we can have n plus 1. Okay, so using a fractional and divider, in a PLL as before, we can find f output also. Earlier our f output was n into f ref, but here it got improved in this one, and it got changed to f output into f ref into n plus k by r. This is your fractional and divider output. Okay, it control logic and is operating at f ref only. Okay, reference frequency can be greater than the step size. That's good. No. Okay, that's now you can see we have an example here, not given an example, but we have a range 440 megahertz to 450 in 25 kilo. Now this time f reference is 10 megahertz. Choose n and r. F references, F, we can have choose N and R. Okay, we have the step size formula also. We have minimum equal to N ref and F ref, minimum frequency, and we have step size equal to 1 by R F ref. Okay, these are the formulas. Okay, now we can see problem with fractional PLL. Till now, do you have any doubt? Then ask me. Because I think I'm moving very fast. If you have any doubt, then ask me.
I don't know. I don't really understand this. I think I'll have to study it myself. So,
Sorry.
I don't know. I'm not really understanding this chapter, so I'll probably have to.
Okay, so then ask me what you didn't understand. Then because I'm going ahead and you can ask me.
I
Or
don't. I don't even know what to
is it
ask.
too, yeah? Other day you will ask.
What?
Yeah, ask me. Do
I
you have any
don't
doubt?
even know what to ask. To be honest, I'll have to.
Sorry, I'm not getting you.
I said I don't even know what to ask. To be honest, I'll have to study it.
Okay, okay. Point is that are you getting the concept or not? My point is that.
Not really.
Okay, then I'm just moving ahead and you're not asking anything. See, you understood PLL or not? Phase lock loop.
Like I don't understand. Like why? Like what is that used for or anything? Like, I don't know.
Why we are using PLL? You don't know. Hello.
Yeah, I don't understand. No.
Okay, then why didn't ask at that time?
Because it's hard for me to ask you what's wrong. Like I have to sit down and study it myself. Because
Okay. Okay, then can you do one thing? You can revise it once and you can ask me question, right?
yeah,
Because I'm going far and far. Because currently I'm in the frequency synthesis part. So if you'll not understand the other part, it will not useful for you right now, right?
yeah,
And before PLL, have you understand other things, that the free space propagation and all those things? Those part you understood or not?
yeah,
That PTGT one,
yeah,
antenna gain and all those things. I think that till that part you understood everything, right?
yeah.
Okay. So can you in this week, can you do one thing, one thing? You can just revise all things, just 1 dB compression, 3 dB IIP3 and all those things, and PLL up to PLL, the
Okay,
of your last class notes, that your first unit PDF, that PLL part, and after that, if you'll not understand, then you have to ask me. Okay,
okay.
because in this way I can cover every syllabus and it will be not useful for you, right? You have to write exam, right?
Yeah,
Because I am going ahead and I was thinking that you are getting it everything. So it's better. You can revise PLL, okay, from your
mm,
last unit part, and after that study it, and after that please ask me what you not get and what you are getting it, so I can make it more clear to you. Okay.
yeah.
Okay, any issue in that?
No, that's fine.
Yeah, I think then we can close today, and
Okay,
yeah, we can, once you revise it, just pin me in the weekdays also. I can do one thing in the
okay,
in some of the weekdays. You can pin us and we can take up 1 hour class so
okay.
that I can clear your all doubts. Okay,
Yeah, that works.
that will work. And from next Saturday, Sunday, we will take up this unit once again. Unit
Okay, yeah,
number 2, the PDF that you have sent it to PDF you have sent it. Okay, first my intention, you complete all the topics that you not understand in the last unit?